Okay, in this video we need to talk about something called Bohr's hydrogen atom. So this guy Niels Bohr, another German physicist, in 1913, so a little over 100 years ago, basically figured out that in terms of trying to figure out how electrons move around, he took some of the ideas of classical mechanics, like angular momentum of things moving in a circle, because he visualized like the planetary model, but also the quantum mechanics thing where things can only have certain values, like we saw in line spectrum, and he tried to make those ideas fit together. Okay. So he based this all off the planetary model. Okay. The idea is there was some sort of nucleus in the middle. I'm going to just draw it as a dot. And electrons flew around the outside in very, very specific orbits. So like with the solar system, there's the sun in the middle, and then there's Mercury, Venus, Earth, Mars, Jupiter, whatever. Okay, but those orbits are kind of almost random. They could be anywhere, really. They are where they happen to settle. But it turns out that for atoms, only very, very specific values are allowed. Okay, so it can only be at certain values. And what he did was he tried to figure out what those values are. So the innermost one, he just kind of numbered them. This is n equals 1. The second one is n equals 2, so on and so forth. They do actually somewhat get closer together as they go along. My picture's probably not going to represent that well because I can't draw. And so on and so forth, okay? It just keeps going and going and going, however many there are, okay? What he did was he was trying to explain how this correlates to those line spectra that we saw in the last video. So what he said was that anytime you have an absorption, what's happening is it's actually an electron moving from one orbit to another. So an absorption could be an electron that's in the first orbit moving to the second orbit. Okay, it can't end up anywhere in between those two orbits. It can only be on these nice whole integer numbers. Or it could be from the first to the third, or the first to the fourth, or the second to the third, or the second to the fourth. And the idea is each of these energy differences corresponds to one of the lines in the line spectrum. Okay, so if you have the wavelength, you could solve for frequency, and if you have the frequency, you can solve for energy, and these have an energy difference. Okay, so basically absorption is electrons moving from a lower orbit to a higher orbit. And to do this, it requires energy. Okay, energy in the form of light or heat or electricity or whatever. Okay, so if you put energy in, what's going to happen is these electrons can move from these nice stable lower orbits to higher energy orbits. Okay, they're basically only specific values are allowed. Okay, only specific orbits exist. Okay, they can't be just anywhere. There's only, the universe just happens to line them up, so there are only very, very specific options. Okay, and to do this, you have to, this requires energy. Okay, but the idea is that if you had a line spectrum for an atom, the individual lines you're going to see correspond to very specific electronic transitions. Okay, it's called an electronic transition when you're going from one orbit to another. Okay, so these little arrows are called electronic transitions. Okay, and if you have an emission spectrum, I guess I'll try to keep my colors consistent here. An emission spectrum is kind of the same idea. And I guess for the sake of comparison here, I'm going to try to keep things color-coded here. So an emission is when you have an electron moving from a higher orbit to a lower orbit. My pen is dying. Well, I was going to color coordinate this. Well, that failed. Okay. Go with red. Sorry, red's not a great color here. So from a higher orbit to a lower orbit. Okay. And again, these only exist, they're only at specific orbits. And it turns out that they are exactly the same n values, the same orbits as for the absorption. This releases energy in the form of light. Okay? But it's the exact same differences. It's the exact same electronic transitions. So whether it's an arrow up or an arrow down, it's, yeah. So for absorptions, it was going from a low orbit to a higher orbit. For this one, it's going from a higher orbit down to a lower orbit. Okay? I can't draw straight lines apparently, but you know, whatever. Yeah, and so on and so forth. I only drew up to n equals 3. There's obviously larger numbers. Okay, but you'll notice that whether the electrons are coming or going, the distance between these orbits is constant, and that's what corresponds to the line spectrum. Okay, the difference between these different orbits. Okay, so if you had an absorption spectrum, what's happening is you're shining white light on it, and any frequencies that correspond to a specific transition, like from n equals 1 to n equals 3, whatever that energy difference is, that energy will be absorbed by the electron moving up, and so that will disappear from the line spectrum, from the continuous spectrum. Similarly, if you electrocute an atom, all the atoms are going to get bumped up to higher energy, and as they fall down, they're going to make very specific drops. Okay, and a drop from 2 to 1 is a very specific frequency, and that's what line what wavelength of line you're going to see. Okay, so what Niels Bohr did was he took this concept and literally this one particular line spectrum. He only worked with hydrogen. Sorry, it's not focusing. So he had 1, 2, 3, 4 lines. That's all he had. He basically derived an entire equation to allow us to predict any electronic transition for hydrogen. Pretty narrow range, but yeah. So he won a Nobel Prize for this. I'm going to show you the equation, then we'll talk about the Nobel Prize side of things. So the equation is not all that horrifying, actually. I'm not saying it's super fun, but it's not really... Considering how complicated the situation is, it's not that bad of an equation. So this is the energy change. This is an electronic transition. It's equal to B, which is some constant, Bohr's constant, oddly enough, divided by whatever the initial n value is, squared. So 1 over n initial squared minus 1 over n final squared. And those n values are our nice whole numbers that we saw here. Okay, so this is, he won a Nobel Prize for this equation. Okay, delta E is the energy of an electronic transition. So how much energy it takes to move from one orbit to another. Okay, and the units are going to be in joules. B is Bohr's constant. It's just kind of there to make everything work out. But it's 2.179 times 10 to the negative 18th joules. Very, very small number. Okay. And n initial, or ni, is the initial orbit. It's just going to be a nice whole number. And n final is the final orbit. These are going to be whole numbers. Okay. So let's try an example. Okay, and just see how to apply this. Oh wait, let's talk about the Nobel Prize. Okay, so this guy won a Nobel Prize, but more importantly, he also happened to live right next door to a brewery in Germany, and they thought his work was so freaking impressive. He was like a rock star for his age. They thought he was so impressive that they literally ran a pipeline from the brewery to his house, and they basically said, you have an unlimited supply of beer. Here you go. So on top of winning a Nobel Prize, which is, you know, like $1 million, he also won a lifetime supply of beer. Anyway, random anecdote. So let's try an example. we want to know, we want to calculate the energy of an electronic transition from n equals 5 to n equals 3 in a hydrogen atom. I will point out that all of this stuff that we've talked about only works with hydrogen if you only have one electron. We're going to extrapolate and make some generalizations in the next part, but for right now, it only really applies to hydrogen. So what this question is asking us is, if we started out at 5, basically whatever the 5th orbit out, and we drop down to 3, what's the energy difference? Okay, what's the energy of that electronic transition from falling from 5 to 3? Since it's falling from a high energy to a lower energy, we can see that it's an emission without even doing any calculations. Okay, so we plug it in this equation that's up here, and we see what we get. I'm gonna rewrite the equation real fast. Okay, B is 2.179 times 10 to the negative 18th joules. 1 over, make sure you square these when you're doing these problems. So n initial was 5, 1 minus 5, or 1 over 5 squared minus 1 over 3 squared. So, typing this in your calculator, be really careful with the scientific notation going on, but 2.179 second EE negative 18, okay, times, I'm going to put it in parentheses, 1 divided by 5 squared minus 1 divided by 3 squared. Close the parenthesis, should be that, right? We get a really low number, but we get negative 1 point, I guess that, this, there's not really sig figs on this. This has 4 sig figs, so I'm gonna do this to 4 sig figs. That would round up to, delta E would be negative 1.550 times 10 to the negative 19th joules. So it is a really, really small amount of energy. Okay. Okay. So let's say that's part A. Part B. Is this an emission or an absorption? Okay. There are 2 ways to look at this. We kind of spelled it out earlier, but you're going from a high energy to a low energy, which should be an emission. Okay? Or this actually works like it did in the last chapter. This has a negative value, which means that it is releasing energy, which is something that happens during an emission. It's emitting the energy. So the answer is, and it's an emission. So you can look at the sign of this, or you can look at the going from 5 to 3. Either way, it should be consistent. Okay. Now we want to know, what is the frequency of this photon? So it's emitting a photon. We want to know what's the frequency of it. Okay. Well, we have an equation, E equals h nu. I know we solved this equation, haven't done anything with it yet. That's okay. This is the energy of the photon. The negative tells you that it's leaving, but the energy has to be positive. So I'm going to plug it in as positive 1.550 times 10 to the negative 19th. Okay. We're solving for nu, so I'm going to divide h to the other side, and nu equals E over h. So E is 1.550 times 10 to the negative 19th joules. H is 6.626 times 10 to the negative 34th joule seconds. Wow, that looks terrible. Negative 34th joule seconds. Joules will cancel out, and you end up with 1 over seconds, which is great because we're solving for frequency. Okay, so 1.550 E negative 19 divided by 6.626 E negative 34th. And I got 2.339, I guess. 2.339 times 10 to the positive 14th inverse seconds. So that's the frequency. Okay. Let's say, what is the wavelength? It's all related. Okay, well, now that we have the frequency, lambda nu equals c, C is a constant, nu is what we just solved for, lambda is what we're solving for, so we're going to divide nu to the other side. C is 2.9979 times 10 to the 8th meters per second. This value we just solved for is 2.339 times 10 to the 14th inverse seconds. Inverse seconds will cancel out and you're left with meters, which is great because we're solving for a distance. So if you type all this in, I don't know how well you can see all this on here, but that's okay. 2.9979 EE8 divided by 2.339, oops, not that, EE14, we get 1.282 times 10 to the negative 6th. And then that's meters. Okay. If we translate this, that's 1,282 nanometers. So if we look back at our visible spectrum that we had in the thing the other day, the visible spectrum is from 400 to 750. So this would not be a color that we could see. It would be higher in wavelength, which is lower in energy than our visible spectrum. So it would actually be slightly in the infrared region. So the electronic transition from n equals 5 to n equals 3, okay, is technically in the infrared spectrum and we can't even see it. But this is how you would do all the math to figure out what the energy is for that electronic transition. All right, thanks.